All right, so again, what I want to do is I want to do a really quick breakdown of writing equations, balancing equations, and doing net and complete ionic equations. Okay, so when we have an equation, remember it's A goes to B, and A are reactants, and B are products. The big deal about equations is that in order for them to make physical sense, they must be balanced. I like to talk about them as telling a story, and the story is about how the reactants change to products. You can tell that story without it needing to make physical sense, in the sense that it's fiction. If it's not balanced, it doesn't matter. It's just fiction. You can still tell the story. But if you want it to be nonfiction, if you want it to be based in physical reality, you have to balance the equation. And so what I mean by that is this. We can have a story that says hydrogen and oxygen are what makes water, or you can have a reaction where those things get together and make water. So this is sort of the fictional version of the story, because if you notice, it can't be based in actual molecules and atoms, because I have 2 hydrogens and 2 oxygens there, but only 1 oxygen on the product side. So in order to turn it from fiction into nonfiction, or from fiction to nonfiction, I have to balance the numbers and types of atoms on both the reactants and product side. So I have oxygens and hydrogens, and they have to be in the same quantity. So I've got 2 there for hydrogen, 2 for oxygen. On the product side, 2 hydrogens, but only 1 oxygen. So the basic process of balancing involves using stoichiometric coefficients. What students often get confused about is, what does it mean when I write down a stoichiometric coefficient? Well, before it meant that I had 1 water molecule. Now that I've written down the 2, it means I have 2 of them. And so that changes every atom that's involved in the formula. So if I wanted to say, okay, I have 2 hydrogens and 1 oxygen, I'm going to use a stoichiometric coefficient of 2 to change the number of oxygens. Now I have 2. I also have to recount the number of hydrogens. I don't have 2 anymore. Now I have 4. So before, the hydrogens were balanced, but now they're out of balance. And so in order to balance the hydrogens, I have to come back over here and use a stoichiometric coefficient of 2. This is what we're doing. Now, in this particular lab, we're going to be focusing on mostly ionic compounds. And so let's take a look at that. If I take something like sodium hydroxide and mix it with, let's not use that as an example. Let's just use sodium chloride and silver nitrate. What I want to do is I actually want to add state symbols. So let's say that we have an aqueous solution of sodium chloride and an aqueous solution of silver nitrate. And we pour them together. Now, in the lab, you're going to see an actual video of what happens, so you can see if there's a change and a chemical change. But ultimately, what we rely on is solubility rules. And the solubility rules say this: anything that has a chloride ion is soluble, except when it's with the following cations: lead 2, silver plus, and it'll say mercury 2, but we don't usually deal with that one. Now, how do I complete the reaction for an ionic equation? I'm going to rewrite it, and I'm going to rewrite it in a fictitious sense. So what I need to do is get rid of this solubility rule, but I want you to remember Chlorine is soluble except when it's with silver. And ultimately what you're going to see is that I get it together with silver. Bear with me a second. So I'm going to use that fact in just a second when I finish this reaction. But how do chemical reactions with ionic compounds work? It's this way. Okay. A and C are cations, and B and D are anions. And so if I were to do the same thing and label it over here, the sodium is A, the chloride is B, didn't need parentheses. And here the silver is C and the nitrate is D. How does this work? The bottom line is they swap partners. Cation A will move and get together with anion D. Cation B will get together with anion B will get together with cation C. And by convention, we always list the cations first. So it'll be AD and CB. Now, the thing is you have to use it is double replacement. That's exactly right. You have to use your knowledge of chemical symbols and formulas from nomenclature to put together these formulas correctly. And so if I'm going to do this, that means that sodium ion and nitrate ion will get together. Well, if I'm going to make a compound for it that's neutral, I need one of each because it's +1 and -1. So if we're going to do the cross down, in this case, I'm crossing up, it looks like that. Same thing with silver ion and chloride ion. It'll be AgCl. Now I have to predict the formulas, or I have to predict the states. Well, I'm not really, I haven't really told you all of the solubility rules. You'll have to look them up. But sodium nitrate is definitely going to be soluble. Silver chloride is not going to be soluble. Remember what I said before? Chloride is soluble except with silver and two other things. And so it's actually going to form a precipitate, a solid precipitate. So how does this work? It works, you'll see it. It'll be cloudy in the solution. Two clear and colorless solutions get mixed together, and there's a cloudiness that happens, a white cloudiness. And that cloudiness is the solid. So you can predict what will happen based on solubility rules, but you'll also be able to see what happens based on what you see in the videos. Now, I picked this one on purpose because if you think about needing to be balanced, you have sodium ion, you have chlorine, you have silver ion. And what I tell my students is that because nitrate does not undergo a chemical change, it stays nitrate. If you want to use a list, eventually you need to get away from using lists, then what you need to do is you need to make sure that it's easier if you just write down nitrate as an ion, a polyatomic ion, rather than breaking it up into a nitrogen and 3 oxygens, because it doesn't change formulas. You can just balance it as a unit. Well, there's one nitrate there and one nitrate there, so we're all balanced. There's one silver and one silver, so we're all balanced there. One chlorine and one chlorine, we're all balanced there. One sodium and one sodium, so we're all balanced there. I picked this one because the balancing is trivial. It's already balanced as soon as you write the reaction, so we don't need to really deal with that part. What I'm trying to get to is this next part. This is a complete molecular equation. What I want to write down is a complete ionic equation and a net ionic equation. And this is the part that's going to be, if you haven't seen it, it's definitely going to be a big sort of a challenge for you as far as being really new. Okay, what is the complete ionic equation? I'm going to use the molecular equation to write the complete ionic equation. But the complete ionic equation talks about the actual individual ions as they are in the solution. And so one of the things that you have to know is that in a solution of aqueous ions, the ions actually in a compound like sodium chloride, they don't actually just sit next to each other like this. They actually get to sort of float around the solution and move around each other. So they're not like this, they're more like this. And kind of floating around and moving around each other. And they're surrounded by water. And this is what it means to be dissolved, is surrounded by molecules of the solvent. And I want to leave it there. So this is a crude picture of what it looks like to be dissolved. And so what we want to do is we want to tell the reader what that means and what it looks like. And so this is how you do it. I would say I'm just going to go one by one in the equation and write everything down exactly as it appears, but as it appears in the solution from the perspective of the ions. So that means I have a sodium ion and it's aqueous. I have a chloride ion and it's aqueous. I have a silver ion and it's aqueous. I have nitrate and it's aqueous. See, I'm looking at the states. That's why it's important. And then on the product side, I still have an aqueous sodium ion and I still have an aqueous nitrate ion. But look what happens here. They're no longer aqueous, they're solid. And since they're solid, they absolutely do stick together. They actually do make a solid particle of silver and chlorine stuck together. So I want to tell that to the reader. I have a silver chloride solid. So what I'm doing with the complete ionic equation is I'm telling the reader exactly how things appear in the solution from the perspective of the ions. If they're aqueous, then they actually are floating freely and not associated with each other. And so I write them as if they are sort of broken up and floating freely and not associated with each other. If they're solids, liquids, or gases, they're actually together as a compound, and I need to write that down that way as well. So what the net ionic equation does is it tells us what actually happened as far as the chemistry is concerned. So what I do in order to write the net ionic equation is I take the complete ionic equation and I cancel out anything that appears on both sides of the equation in exactly the same form. So sodium ion is by itself an aqueous, nitrate ion is by itself an aqueous, I cross those two things out. Then for the net ionic equation, I write down what's left. And just by convention, I'm going to swap the position of those two things because I typically just like to write cations first. It doesn't actually matter. You're not wrong if you don't swap the positions. But the story, the net story, is that a silver ion that was aqueous finds a chloride ion that was aqueous and then makes a solid silver chloride. So this is complete molecular equation at the top, taking the complete molecular equation, turning it into an ionic equation, and then taking a complete ionic equation and turning it into a net ionic equation. You'll notice that as long as it's balanced here, once it's balanced in the complete molecular equation, it'll be balanced here and here, here and there, as long as you write down all the correct stoichiometric coefficients. Let's do two other quick examples, and I'm going to go faster without explanation in this case. What if we had something like let's do lead acetate. So let's do lead 2 acetate. So lead 2 acetate would be PbC2H3O2 aqueous plus let's do sodium chloride again, NaCl aqueous. And then let's swap their partners. And so this is, again, the double displacement bit. And so here's A, here's B, here's C, and here's D. Remember that I want to write down AD plus CB. And so what is A? A is lead 2. What is D? It's chloride. So how am I going to write the formula? It should be PbCl2. What about C? C is sodium ion, and need a 2 here. What is B? B is acetate, C2H3O2 minus. So what's the formula for that one? NaC2H3O2. And it will be aqueous based on solubility rules. This one will be solid based on solubility rules. You are in class, Ria. You've been in class. Again, you would see this you would see the fact that lead chloride forms a solid because you would notice a precipitate being formed. All right, so there's a couple of things I just want to mention before I get to balancing. I noticed there are two acetates here. This was in the formula. There are not 2 acetates there because that's not the formula for sodium acetate. Students often get confused. They just want to write down the same numbers of things. But remember, the formulas of compounds are formed based on nomenclature rules. And that's like the cross down game, or making sure that the charges are balanced. So once I've done that, now I can balance though. Now I can balance. I still want to balance everything in terms of the number of atoms being the same on both sides, but I don't change the formulas. I use stoichiometric coefficients to do that. And so how many leads are there? this is the last time I'll do this one. How many sodiums are there? How many chlorides? Leads. How many acetates are there? Remember, that doesn't change formulas, so I don't need to do anything with it. One here, two here, one here, one here, two here, one here, one here, one here. So it looks like leads are good. I need to balance these. So I want to put a 2 there in order to change this to 2. Now I have 2 acetates, but what else did I change? Remember, now I've changed the number of sodium ions. So I went from 1 to 2. Okay, well then let's continue to work on balancing things. Well, chlorine is 2 here and it's 1 there. And also I've now changed sodium, so it's 2 and 1. So that means if I put a stoichiometric coefficient of 2 there, then I'll be set. I'll get all balanced up. Okay, now that I've done that, I've got a balanced molecular equation. I can write an ionic equation. I know I'm going fast. I'm going to post the video. Hopefully you'll be able to review it instead of like getting crazy with the speed. All right, how do we have it? What does it look like? I've got a lead 2+ ion and it's aqueous. Here's the part that gets confusing for students. I do not write this. I write it like this. 2 acetate ions, and they're aqueous. Now, I'm going to do the same thing with the stoichiometric coefficients here. 2 sodium ions, aqueous, plus a chloride ion, aqueous. This is a solid, so I'm going to leave it exactly as it is. Lead chloride, solid. And then I need to take some extra room here. 2 sodium ions, they're aqueous. And I have 2 acetate ions, and they're aqueous. There's my complete ionic equation. Notice I list all the charges. This is something that students often forget as well, the charges. You need to have those charges. So let's cancel everything out that appears on both sides of the reaction to write the net equation. And so that means what's left is the net equation. So I have lead that's left. I have a chloride that's, oh, look what I didn't do. Look what I didn't do. You see that there? So let's just change that up just a little bit and correct that. 2 chlorides. Hopefully you caught that. Hopefully you caught that. Okay. So I have 1 lead, I have 2 chlorides, and they form lead 2 chloride. So the net ionic equation is Pb 2 plus 2 Cl minus. This is aqueous, and they form PbCl2 solid. Okay. All right, I'm going to do one last example, and it's going to be really fast. It's going to be faster than that. I'm not going to even write the list down for balancing. So that's an example of some double replacement reactions in terms of ionic compounds. There's another type of reaction that you probably will encounter in this particular lab, and it's hold on a second. It's an acid-base reaction. And so I'm going to show you an example of an acid-base neutralization reaction in terms of these complete and net ionic equations. Let's do aluminum hydroxide aqueous plus sulfuric acid aqueous produces, and acid-base reactions always produce two things: water, liquid, and a salt. And the salt will be based on that ion and that ion. It's because the hydroxide and the hydrogen ion are what get together to make water. So I'm left with the sulfate and the aluminum ion to make the counter salt, the salt that's formed. And so the formula for that would be Al2SO4 3. And I'm going to ignore solubility rules for the moment. I'm going to say it's aqueous. And I'm doing this just for example's sake. Now that I've written down the equation, what I want to do is balance it. And so I've got a lot of work to do because there's a lot of stuff that's not balanced. I have two aluminums here, so I need two aluminums there. I have three sulfates here, so I need three sulfates there. It looks like I'm starting to balance everything out. Now let's deal with the oxygens and the hydrogens. I've already took care of all of the oxygens and sulfate. Remember, I'm balancing that as a unit, so I don't need to worry about them. But I do need to think about these hydrogens, those hydrogens, and that oxygen, and they're all in the water. So there's a couple of different ways to do it. You could say I've got 3 times 1 here for hydrogen, 3 times 2 there, and so that's a total of 12. So 6 times 2 would be, so it's 3 times 1 times 2. That's a total of 6 on that side, 6 over here, 6 over here, that's 12. So that would work. 6 times 2 is 12. I could also look at it from the perspective of the oxygen. 3 times 1 is 3, times 2 is 6, so I need 6 oxygens. Either way, I've now balanced the equation. Ultimately, your goal is to be able to do it that fast without any sort of list. All right, let's do the net equation. This one's going to be a little bit longer. 2Al3 plus aqueous plus, now look what I have to do. The formula itself has 3 hydroxides, but I have 2 of the formula. So that means I have 6 hydroxides that are aqueous. Now, how do I break up an acid? Remember that the H's are H+, so 3H plus aqueous. Oh, not 3, it's 3 times 2, so that's 6H plus aqueous plus 3 sulfate aqueous. Now I can write the products. Water is a pure liquid. That L means I just write it down exactly as it appears. And now I can do everything else. So I've got 2Al3 plus aqueous plus 3SO4 2 minus aqueous. Now I'm still going to cancel out everything that appears on both sides of the equation, and I'm going to write down what's left. So I get, for the acid base, the net ionic equation, 6H plus aqueous plus 6OH minus aqueous produce 6H2O liquid. And so that's what you're going to be doing. That's how you do it. And I know that that was breakneck speed. That was real fast. That was no questions asked. That was go from basics to advanced skills all within about 40 minutes. Actually, it was more like 25 minutes because we kind of dallied with talking for about 20 minutes. So I'm going to stop the recording there, and that's what I'll post.